everybody. I'm going to speak about the supernova event 1987A, but this is a small part of a more extensive project of research I am really looking forward to doing in the next future. And I will tell you what it is about in a few moments. And of course, for this future research in particular, I will be, every suggestion from this distinguished audience will be very much welcome. So, as you all know, the supernova 1987A was an extraordinary event in astrophysics. It has been a true cornucopia of discoveries and of investigations up still today. It holds a lot of scientific records. As you know, it has been the brightest supernova since Kepler's supernova of 1604. It has been the first supernova to be observed in every band of the electromagnetic spectrum, and it allowed the first detection of neutrinos coming from a core collapse. It was also the very first time that neutrinos coming from a celestial body other than the Sun were detected, and this was the start, was considered the start of neutrino astronomy. And it was the first time that it was possible to identify the progenitor star on the archival photographic plates that gave birth to the supernova explosion. It was also the first time that scientists could observe supernova nucleosynthesis, and of course, very importantly for gravitational wave emission, it was the first time that one could look at the geometrical asymmetry of the explosion, so the non-spherical explosion. Of course, this is an image of the supernova in the different electromagnetic wavelengths seen by different instruments. You have the radio telescopes, the ALMA radio telescope array, the Hubble Space Telescope, and the Chandra X-ray Observatory, which give these images. Of course, something for gravitational waves, also we have some very different signals coming from different sources. And of course, the frequency, as for electromagnetic waves, the frequency band is very important. You can see some kind of theoretical signals of gravitational wave signals coming from different sources, binary systems, so continuous sources with a continuous constant frequency. You have binary systems at the end of their life, with the final coalescing phase, with a frequency that is very rapidly growing in time, and also in the signal is growing in amplitude very fast. And you have supernova with this kind of peak around a particular frequency. And also, also for these kind of sources, you can have different kind. Oh, I'm trying. Okay, you have different instruments that can look at these different frequency bands and different signals. And the first generation, as Dan has said before, of gravitational wave detectors were a creation of Joseph Weber, and they were resonant bars. Then we have a second generation of resonant bars that were the ones cooled to low temperature, and we have an example here, the Explorer antenna that was built at CERN by the group from Rome, led by Edoardo Amaldi and Guido Pizzella. And this kind of instrument is, for its principle, working principle, is something that resonates at certain frequencies, and so it has it is sensitive to a very peaked frequency. So it is an instrument for which the best candidate for source for detection are, of course, is supernova. And then you have the second generation detectors, which are the interferometric antennas, as you have seen, the LIGO and Virgo, and you can see the huge change of scale. Explorer was transported to Virgo in Kashina, and that small red circle that you see in the image is Explorer, close to Virgo. This required really a great change of scale, not only in the dimension of the apparatus, but also in the funding and in the scientific collaboration in the people involved. And then we have the future space interferometric antenna in LISA. As you can see, the frequencies to which these antennas are sensitive are very different. We go to very low frequencies in space thanks to getting free from seismic noise. So what is my these are my questions, and which is part of my future research. I am very interested in the progress of astrophysical observations and astrophysical models for sources of gravitational radiation. I'm very interested in how did the knowledge about the candidate sources of gravitational waves develop and influence the development of gravitational wave detectors. How did the transition, in some sense, of the interest of gravitational wave physicists from burst signals to broad spectrum astrophysical sources such as pulsars, binary pulsars, coalescing binaries occur? Because of course the interferometric antennas are the ones that can follow a signal that is evolving in time. This is not possible with a resonant antenna with a bar. So this is crucial in the change of perspective and the change of detectors. And how did the experimentalists developing gravitational wave detectors interact with astrophysicists and theoreticians in this respect? This is very interesting in my point of view, and it is not completely clear how things got. So at the end of the 70s, there was this nice 2-week workshop in Seattle devoted to sources of gravitational radiation, which gathered some of the prominent workers in these fields. But which are the fields? The introduction says this field, the research on sources of gravitational radiation, has grown up as a number of fragmented specialities with little communication between them. In a raw manner, one can group the measured specialities into 4 areas: astrophysics, theoretical relativity, numerical relativity, and experimental relativity. And that's interesting to look at the papers devoted to the different arguments. We have 7 papers devoted to black holes, 5 devoted to stellar collapse and supernova, and 2 devoted to binary systems. And it's interesting also that, as Dan has said before, that the accurate confirmation of the gravitational wave emission by the binary of Holtz and Taylor was still to be achieved. It would be achieved in the early 80s. So it was still something which everybody was looking forward to. So, and at that conference, Braginski pronounced some very, I think, illuminating things. He was a pioneer of gravitational wave detectors in USSR, and an experimental physicist, but with also a theoretical physicist, kind of. But he is speaking as an experimentalist here, and he is saying, first, with regard to resonant aluminum and crystal bars, we must have more detailed waveforms in the kilohertz band from theorists. Experimenters need to know at least the following. How often do various kinds of catastrophic events occur, supernova, in different kinds of galaxies? There is a need for some agreement among theorists on this point. This is crucial, of course, for experimentalists. They must know the most probable mean values of the signal frequencies in the 1 to 10 kilohertz band in order to know where to tune their antennas. Also, how are the frequencies of these bursts distributed? Is it best to concentrate near one frequency or to spread out? How often will supernova be too symmetric to radiate with a detectable efficiency? Finally, what other observable events, electromagnetic and neutrino, accompany gravity wave events? Theorists must provide the knowledge needed by the experimentalists who must ultimately apply optimal filters and the theory of pattern recognition to their data. This is very much a comment that reflects very much also some comments made yesterday by Alan Watson and Christian Spearing in their own fields, neutrino astronomy and gamma ray astronomy. The problem of the lack of theoretical models in some sense. So, of course, these were the big issues in supernova gravitational wave detection. The conversion rate of energy irradiated in the shape of gravitational wave emission, it was not clear, and it continued to change, this conversion rate, starting from 10 to -3, and in the years becoming less and less, going to 10 to -11, and things like that. And also the statistical occurrence of supernova, which could be detected through gravitational wave detectors. As Sergio Frasca said, this is something that reminds Alan Watson and Christian Spearing yesterday comments. In the end, the reason why we went ahead, Sergio Frasca has been a member of the gravitational wave group in Rome since 1976. So he commented in an interview, in the end, the reason why we went ahead with our experimental research on gravitational waves, cryogenic part detectors, is that every time we did another upgrade and we didn't see anything, there were some theorists who told us that just a little more sensitivity would be needed and then waves would show. If 40 years ago someone would have told us what the sensitivity really needed to be achieved was, nobody would have been so crazy to get involved in such an undertaking. So, however, let's go to our story. Of course, everybody knows what happened on the February 23, 1987. A Canadian astronomer working at the Observatory Las Campanas in Chile, and I'm happy to show this. Yesterday there was a beautiful talk by Barbara Silva on the observatories in Chile. He was the first one to see the appearance of this supernova in the Large Magellanic Cloud. And okay, I show you just where the observatory is. And of course, this was not visible from the northern hemisphere, but in the northern hemisphere, there were the neutrino detectors, IMB, and then the UNO on Mont Blanc underground neutrino observatory, and Baksan neutrino detector, and of course, Kamiokande. And when they received the news about the appearance of the supernova, they immediately went to see in their the data in the days before. And this is what they found. This is the timeline going back. So the UNO Mont Blanc detector saw these 5 neutrinos in 7 seconds, 5 hours, about 5 hours before the bursts seen, observed by the Kamiokande, IMB, and Baksan observation. Of course, the most significant ones are Kamiokande with 11 neutrinos in 13 seconds and IMB with 8 neutrinos in 6 seconds. And what was unfortunate is that in the world, you see in the US and in Europe, you had these possible detectors, gravitation. Oh, sorry, yeah, I have to run. However, what happened was that the cryogenic bars that were Stanford, Allegro, and Explorer was the only one who had achieved the temperature, the 2 Kelvin temperature and sensitivity, but it was still under maintenance at the time, so it was off. And the only bars that were working at the time were the one by Joseph Weber's at room temperature in Maryland, and a bar that was in Rome at room temperature, but that was not supposed to be a bar for gravitational wave detection. It was for it was an experimental apparatus for studying background of gravitational wave antennas, and so. But when these, the group in Rome was alarmed by the people in Turin who were running the UNO detector in Mont Blanc, they immediately went to see their data because they had only this bar at their disposal, and they found, strangely, they found a signal, or they found something strange at just 1 second, about 1.4 seconds before the arrival of the first neutrino at Uno Mont Blanc. They found a peak, and they also calculated the limits, or the upper limits of the neutrino mass, using this difference in time. And of course, there was a big elephant in the room, but this, everybody was well aware, the group in Rome was well aware of this, that to have a signal detectable by the geograph antenna, you could say that the progenitor mass, the mass of the progenitor star, would have to be many orders of magnitude more than the mass observed astrophysically from the astrophysical estimates. So this, I cannot go into detail, and these there have been many articles published, and there have been some, what happened were also some coincidences, studies between of course, the bars of Weber in Maryland, Rome, and the neutrino detector in Mont Blanc, but there was a huge scientific controversy, as you can see, and only the first paper by the group was published on the Aerophysical Letters, and the other ones were published on Nuovo Cimento. I cannot enter into detail. Okay, and there have been also attempts to make some models, theoretical models, to explain this. Also based on some kind of effect, superradiance, that could change the cross section for absorption of gravitational waves in a massive antenna, but also looking at different models for the sources, the supernova. And this is De Rucola who made this paper just few weeks, months after this coincidence, saying, well, can a supernova bang twice? Because of course it was the strange thing was also the small burst of neutrinos exceeding the background at the Mont Blanc that was preceding about 5 hours the Kamiokande and IMB and Russian observatory. This work is something that we are carrying on with my former student Marco Giganti, who made a thesis in history of physics on this subject, and we are working at a paper to be submitted to EPJH, so next month. However, at that time, a second generation of bars was about a third generation. Sorry, I was mistaken. Of bars was being built. These are the twins. These were the only ultra cryogenic resonant bars in the world, and that were built, Nautilus and Auriga, in Frascati and in Padua, working at 100 millikelvin, so very low temperature. And this was happening, as you see, the years 1994, 1997, when they become operative. This was happening exactly at the same time in which there was the turn in the material culture of gravitational wave research. There were the delicate negotiation for the huge interferometers were going on, and for the construction of LIGO and BIRCO. So these are my questions. I go back to the initial questions because I think this is very important to understand how the models and the knowledge on astrophysical sources impacted the world of experimentalists, and how many interactions there were, because you have also to I need to highlight that the gravitational wave community between the 80s and the 90s was changing scale. Until the 90s, there was not, we could not really speak about the gravitational wave community. There were not dedicated conferences. There were not regular exchanges in some sense. It was, there were small groups. There was not a central coordination or some kind of so everything was surely much different from what then it became later with the creation of the Gravitational Wave International Committee, the GWIC, and with the conferences like the first conferences, Edoardo Amaldi Conference on Gravitational Waves, that became a yearly periodic conference in the field. So I thank you for your attention. I'm sorry to be late in presenting.
Thanks a lot. You were quite on time. There is a comment by Daniel, and then maybe I will give the floor to Christian Spearing, but I will start with the comment. Transients are an important aspect of astronomy, and I wonder if they are one way in which astronomy will continue even when detector improvements are no longer possible, as Martin Albert forecasted. Do you want to reply, or this is maybe a question that others want to?
Yeah, that's interesting. I don't have an answer to this, so I really.
Yeah, I didn't have any comments. It's really interesting though to hear. You know, I've looked at the gravitational wave detection history of these bars, and it's very complex. I'm sure Virginia Trimble is going to be talking about that a bit, I suspect. And it's just, some of these things are heartbreaking. You know, you spend a lot of time building the instruments, and it goes on through your whole professional life.
Thanks
yes,
a lot.
Absolutely. I really understand this. I spent a lot of time with people who have spent their entire career working on gravitational waves, like Guido Pizzella, who is a very talented experimental physicist, and who is continuing to analyze those data of, maybe you have seen, but the last papers published are just recent, because he's continuing to analyze those data, and it's not an easy.
Before Christian, just a second. Before I have to inform Virginia Trimble. Virginia, we see you muted. Maybe I made a mistake myself. So if you can unmute yourself, you should close the phone and call it back. Especially, okay, now you can unmute yourself.
I think I just unmuted myself.
Okay, wonderful.
I guess that was Martin Harwood just speaking a moment ago, wasn't it?
Yeah, wonderful. Okay,
look, I'm very good at, I can't see you guys, I'm on the telephone, but I'm quite good at voices. And I'm so glad Adele mentioned an elephant in the room, because I'm going to mention elephants in the room too.
Okay, thanks a lot, Virginia. Okay, you can unmute yourself, and we are very happy that it works. So, Christian, please.
Yeah, thank you, Adele, for this interesting talk. Particularly for me, the neutrino side was interesting. And you presumably know all the Italian and Russian papers about the two pulse explanation. And I just want to add one explanation which you may not know. It has been made by Gerd Schatz, who was the former chair of the Cascade experiment in Karlsruhe. And he looked for gravitational lensing of neutrinos. And he showed that you can explain it, you can explain the fact that the first pulse was seen only by LSD in Mont Blanc by gravitational lensing of neutrinos. So it was enhanced by a factor of 10 at the LSD side and not enhanced at the other side. That's a very, very special configuration which you request for that. It's much less probable than to explain the 5 events by by chance, but it is not impossible, and I can send you the reference.
Oh, that would be great. Thank you so much for this. I didn't know this, so it's really a great help. Thank you, Christian.
It was made on an European Cosmic Ray Symposium in 2014 and published on AstroPH. I will send.
Thank you.
So there is a question by David Devorking. I think that this is the last we can take before the break, which I think you replied. I mean, did any of the Weber bars detected supernova 1987A? So this is the question.
Yeah, this is this is the question. This is a big question, of course. There was what I said is that there were some coincidences that were seen by the only bars that were working at the time. Unfortunately, there were only these ones that were the Weber bars, yes, and the bar Geograv in Rome. So the question is, did they, the community, the scientific community, did not recognize that they detected them? No. So if this is the reply of the scientific community, what we can say, and of course, I don't want to enter in the scientific thing because there are so many other people that can here say much better than me this. But what happened is surely something strange in the replies. You know, there was this reply by Schultz on Physical Review D, which was very severe in critics on the work and on the coincidences between Weber, Pizzella, and the Mont Blanc detector. And what happened was that the group of Pizzella, for example, I know better that story, wished to reply because they had their own reasons and they took into consideration the critics, of course, but they wanted to reply, but their reply was not published by Physical Review D. And this is something, I mean, there is the right to reply in some sense, or if this is not considered scientifically valid from, I mean, this is a question. At the end, they could not, the possibility of reply was denied. So this is something, of course, and that I can say, and something on which we can reflect.
Thank you very much. And